Okay, now let's try to understand the effects on these parameters. First of all, the Vs, that is your source voltage, it is fixed. Okay, this one is fixed. This is the supply voltage, it is fixed right here. So Vs, this is fixed. Okay. Now let's assume your load is fixed. That means you are not changing the load. Load is fixed. So you are not changing your load at all. So if the load is fixed, if you are not changing your load, the delta should also be fixed. That is, your torque angle should also remain constant. Again, Ns is always fixed. That is the synchronous speed, it is also fixed. So since your Ns is fixed and it is a synchronous motor, the speed of the rotor is also fixed. That means it is also fixed, means constant. It is also constant. And the load is not changing. So since the load is not changing, that means the load is same. The power input or power required is also fixed. The power is not changing. So the P is equals to, that is your 3 V, that is your VIA cos theta, that is the input power. The power that is taken by the input power, the power that is taken by the motor. Since the load is not changing and everything else fixed, that means it is always taking the same power. Okay, so Pin is also fixed. Okay, so your 3 it is fixed, your V is fixed. What about this IA and this cos theta? So first of all, this is your IA, that is armature current, and cos theta is the angle between these two. Okay, cos theta is the power factor. Now the effect is something like this. Say for example, here on other parameter, that is your EB. So what does the EB depends on? Your EB is the voltage generated on the stator by the rotor flux. So it depends on the rotor flux. The amount of EMF generated on the stator will depend on the rotor flux. Okay. So what does the rotor flux is created? It is created by the field current, the DC field excitation. Okay. The DC field excitation you provided in the synchronous motor. The DC field excitation that you are providing in the synchronous motor, this is generating this EB. Okay. So what is the effect of this thing, of this field excitation on all of these parameters? This is what we want to understand. Okay, so I hope the question is clear. Now try to understand here. First of all, these things are external parameter. So IF, that is the DC field excitation, that internal field excitation, has no effect, can have no effect on this one. This is also external, can no effect on this one, not this one, not this one, not this one, not this one. All of these are external parameters. What it can effect on is these two, that is the armature current and the cos theta. Okay, so the question is how it actually affects. Okay, so that's where we have to develop some graphs. Okay, let's do it carefully. First, okay, I have already have one graph. So this is your what we call under excited condition, when your IA is lagging by your Vs. IA is lagging by the voltage, okay, and this is your EB. So if we keep increasing the IF, the value of the EB will increase. Okay, so come here. If I keep increasing IF, that means increase the DC excitation. If I keep increasing the IF, the EB will increase. The value of EB will increase. So if we plot the graph here, this is your V. Okay, your EB was something like this initially. This was your initial EB. Okay, and now we have increased our EB. So let's say it is going here a little bit increase. So if it increases, that means I am creating a parallelogram like this. Previously it was like this, okay, now it is like this. So the ER is now here, it is like going up. Previously it was here, now it is here. This is your current EV, this is your current EV, this is your previous EV. So the IA is 90 degree from this EV. Okay, for this one, let's say the primary one, if I plot it like 90 degree, okay, so this is 90 degree. This was your, say for example, your original IA. Let's name it. This is your EB1, this is your EB2, this is your IA1. Okay, and this was your theta. Okay, now you have increased your IF. As a result, the EB is increased. This is your EB2. Sorry, this is your EB2. This is your EB1. This is your ER2. This is your ER1. Okay, so the ER2 is also changed. So how this one is going to change? If you look at the previous, yeah, so the power is have to remain constant. That means this portion has to remain constant. Here 3 and V is already constant. That means this entire portion is going to remain constant. IA cos theta. Okay, so the IA cos theta value cannot change when you change the field excitation, but internally these two value can change. IA will increase or IA will decrease, and cos theta will decrease or increase, opposite, so that the entire value, the value in total, the multiplication of these two remain constant, something like this. So if I put a straight line like this way, so this is your straight line. Okay, so this is your original IO1. You have increased your field excitation, it has shifted. So according to this line, let's say this line, it is about to go somewhere here, yeah, like this, around 90 degree, always 90 degree, consider it as pure 90 degree. So this is your IA2, and the resultant, this is your theta2, this was your theta1. So as you can see, your theta2 value has decreased. Okay, so if theta2 value is decreased, that means the cos theta2 value is increased, your power factor is increased. The IA2 value, again this one is decreasing, because this line is a straight line, a vertical line, so the value is decreasing. The IA2 value, the current absorbed by the motor, is decreasing. But the multiplication of the two, this portion, this is your IA cos theta, this is your IA cos theta, this is remaining fixed. Okay, so this is the basic thing. If you understand this, everything else is easy. So what is happening here, I am changing the field excitation that you are providing in the synchronous motor. Okay, if I increase the field excitation, what will happen? This one will change. Okay, due to the rotor flux, the voltage induced in the stator circuit will change. This will in turn, the resultant ER value will change. As a result, the theta2 value will decrease, the power factor will increase, the power factor will improve, and this is better, power factor is improving, and the current absorbed by the motor is decreasing. So increase in DC excitation is better because your power factor is improving. In that regard, it is better. Okay, and this scenario is called under excitation. Under excitation. Okay, so what will happen if we keep increasing the IF, that is the field excitation? What will happen? So this new figure, draw another figure now. So this is your original V. This is your original V. Okay, and this is your, say for example, V is fixed. This is your EB2, the last one. Now what you are trying to do, you are increasing it even further. Okay, let's make it like this. The angle, torque angle is remaining fixed. We are not changing the load. Okay, so this is now EB3. Okay, so if you try to take a parallelogram like this way, like now, okay, so it will something comes like this. It will be like this. The resultant curve is like this. If you increase it even further, what will happen? It will become a straight line, simple like this, a straight line. Okay, think of it like this is your EB4. Okay, you keep increasing the IF, it will once it will become a straight line. So the IA will be something like this. This will be your IA. Okay, this line is same as this line in the previous what? This line. Okay, this is equivalent to this line. Okay, the value of IA cos theta is remaining same. The IA is now at 0 degree with the supplied voltage. That means the theta has become 0. Theta is 0 degree means the cos theta is now at 1. That means the power factor is unity. We are at unity power factor. Okay, and the IA is now here. So previously it was here. Gradually it was decreasing. Now it is at its minimum. It is at its minimum. Okay, so this is the normal excitation for a synchronous motor. So what if we keep increasing the EB even further? What will happen? This one will go backwards. This one go like this here. If it go like this, the IA will become like this. Okay, so let's name it IA5. Now the theta is again start to increasing, but now the IA is leading the voltage. Previously it was lagging, now it is leading. Okay, so the theta is now leading. So the cos theta, again power factor is less than 1, again power factor is becoming less than 1, but now it is leading power factor. Previously it was lagging power factor. At this stage it become unity power factor. Now it is lagging power factor, leading power factor, and IA is again starts to increase. So this is the effect of changing the field excitation in your synchronous motor. If you keep increasing the field excitation, and this one is called overexcited condition. This one is called overexcited condition. So if you keep increasing your IF, first it is the underexcited, it gradually becomes normal excited, then it becomes overexcited, and accordingly the power factor goes from lagging to unity to leading. Okay, so this is what you actually did in your experiment. Okay, this is what you are doing in your experiment. You are performing the experiment to test what is the effect of IF on this. Okay, so if we try to plot a graph based on this, this is your IF and this is your IA. Okay, so first when your IF was small, IA was large. Gradually IA comes to the minimum, again it starts to increase. So this curve looks like a V shape. That's why it is called a V curve. What is this point? This is your minimal point. The minimal point is your power factor is equals to 1. Okay, this is your lagging power factor condition. This is your leading stage. Okay, as you keep increasing the IF, it is going from lagging to leading. That means controlling this field excitation, you can convert your synchronous motor from inductive to capacitive. Okay, if you increase the power here, so the curve will look like something like this. If you increase it even further, it will look something like this. Okay, so say for example this is your P1, this is your P2. So can you answer whether P2 is greater than P1 or it is less than P1? Which one will be correct? Okay, this is up to you, this question. So I believe this is your experiment, the first experiment that we conducted. If you go through the video lecture, the video demonstration that was provided, it should be clear now that what you are actually doing.